Magnetic particle inspection reveals surface and near-surface cracks in ferromagnetic materials without damaging them. A technician magnetizes the part, applies a fluorescent particle suspension, and inspects it under UV light. Cracks disrupt magnetic field lines, attracting particles to form visible indications. To ensure complete detection, the part is magnetized in two directions, detecting defects from multiple orientations. This video captures the precision machining of a custom motorcycle fork foot from 42 CRM04 steel using a Quasar MF400U 5-axis center. The process begins with CAD modeling, followed by multi-directional CNC milling. With tool diameters of 16 mm and 34 mm, the machine sculpts complex contours in one setup, optimizing accuracy and reducing manual rework, ideal for creating geometries under tight tolerance demands. Tension spring production begins with coiled wire fed into a CNC wire forming machine. In this setup, the wire, typically high-carbon steel, is straightened and pushed through servo-controlled rollers. Multiple bending arms then manipulate the wire into precise spring shapes through coordinated axis movements. Hooks are formed last, using rotary tools for consistent loop geometry. The WECOIL system monitors feed speed, coiling tension, and shape consistency in real time. Automatic cutters finish the cycle by trimming each spring to size before it drops into the collection tray. This seamless process ensures uniformity and efficiency in mass spring production, especially for applications requiring high elasticity and dimensional accuracy. Thanks to continuous automation, the system minimizes human intervention while maintaining consistent output over long production cycles. "12-meter rebar bending starts with long steel rods loaded into a heavy-duty hydraulic press. The construction-grade rebar is aligned and clamped before being bent by synchronized pistons. Precise angle settings ensure repeatability for large-scale projects. This machine, built by Çingöz Kardeşler in Turkey, automates the entire process, reducing manual effort. Its extended frame allows full-length bars to be shaped in a single cycle, streamlining operations on construction sites where consistency and speed are essential. The DMU200 gantry machines large aluminum frames using 5-axis milling with excellent chip removal and accessibility. A worn Froriep boring mill is upgraded with a new headstock to support modern cutting tools and higher spindle speeds. The retrofit includes adapting the spindle for internal cooling, overhauling linear guides, and integrating a new CNC control system. This modernization extends machine life while enabling precise, high-efficiency machining tasks that meet today's production standards. Twin-pallet 6-axis machining centers handle large parts with deep drilling and multi-angle milling, reducing cycle time through efficient part rotation. Precision meets power in this 5-axis milling operation on a DMG Mori DMU95 monoblock, where complex parts for an Airbus A320 are being machined. The process begins with roughing strategies tailored for optimal material removal. In the first pass, the tool, APDM20 APA, is used to rapidly cut excess material using a Schruppen roughing strategy with an axial depth of 55 mm. The volume mill approach ensures aggressive yet controlled engagement, optimizing chip load and minimizing tool wear. This phase lasts 1 hour and 40 minutes. Subsequent machining continues with another rest material roughing operation. Here, the strategy involves a ball-end mill, Kugelfräser DM, cutting with a P 0.4 mm and AE 0.8 mm over 7 hours and 20 minutes. This careful attention to leftover material ensures a smooth transition to the final dimensions while preserving structural integrity. A third stage incorporates a high-speed cutting HSC pass using a 20 German Marks tool at 0.3 mm AP and 8 mm AE, lasting 1 hour and 50 minutes. These smaller step-downs allow for finer detailing on geometrically complex surfaces. Final material cleanup uses a Kugelfräser M ball-end mill, cutting at AP 0.4 mm and AE 0.3 mm. This extended 7-hour cycle focuses on tight corners and surface finishing. Throughout the process, the DMU95 monoblock's 5-axis capabilities allow the tool to maintain optimal contact angles and access hard-to-reach features without repositioning the workpiece. Its rigidity, thermal stability, and synchronized motion control make it ideal for aerospace components like those used in the Airbus A320. The combination of advanced milling strategies, volume mill, high-speed cutting, and multi-axis movement results in significant time savings and dimensional accuracy. Every toolpath is programmed to maximize tool life while delivering consistent results on aluminum or titanium alloys, common in aerospace manufacturing. The fixture system ensures each part is held securely throughout the cycle, even under high-speed rotation. Coolant delivery is precisely targeted to control temperature and flush chips from deep pockets. The closed-loop control system continuously monitors tool conditions for adaptive adjustments. Each machining step is simulated in advance to eliminate potential errors before actual production. Operators monitor real-time data from the control interface to ensure consistency. This integration of software, hardware, and human oversight results in dependable, repeatable outcomes. This is water cutting on the move, an industrial process that harnesses the force of ultra-high pressure water mixed with abrasives to cut through tough materials with precision. Abrajet, developed by Wattec AS, uses a mobile 3D water cutting system, allowing it to operate directly on-site for a range of applications. At the core of this method is cold cutting, where water is pressurized up to 700 bars. That stream passes through a focusing nozzle, carrying abrasive particles that enable it to slice through materials from just 1 mm up to 150 mm thick, whether it's steel, concrete, or pipe bends. Offline programming is used to design each cut in advance, enabling highly accurate CNC-controlled movement. The system is versatile enough to cut complex pipe geometries or flat concrete surfaces without introducing heat or distortion. This makes it ideal for jobs where structural integrity must be preserved. One advantage of abrasive water cutting is that it causes no thermal stress, unlike laser or plasma cutting, which can create heat-affected zones. This allows for cleaner edges, no hardening, and better downstream processing. Abrajet's mobile units can reach construction sites, manufacturing plants, or even remote locations, reducing the need to transport bulky workpieces. Whether working on-site or in a controlled facility, it provides consistent performance and clean results across a wide material range. Its adaptability across different environments and materials makes it an essential solution for modern cutting challenges. A 1,600-ton press crankshaft is reconditioned using a SCOD roll turning lathe for precision. This video offers an in-depth look at the CTX Beta 2000, a high-performance CNC turning center designed for precision machining of large components. The process begins with securing workpieces up to 600 mm in diameter and 2,000 mm in length within the machine's expansive working area. The main spindle delivers a robust 2,200 Nm of torque, enabling efficient material removal even with solid drills measuring up to 80 mm. The VDI-50 turret, equipped with 12 driven tool positions, operates at speeds up to 4,000 revolutions per minute and provides 85 Nm of torque, facilitating complex milling and turning operations. An optional Y-axis with plus or minus 75 mm travel allows for eccentric machining, enhancing the machine's versatility. Steady rests support workpieces up to 350 mm in diameter, ensuring stability during processing. Throughout the machining cycle, the CTX Beta 2000 maintains high precision, thanks to its thermally stable design and active cooling systems. This setup ensures consistent accuracy and surface quality, making it suitable for applications in industries requiring thorough standards. The rigid 238P soil pipe cutter is designed for efficient pipe cutting, especially in tight spaces. This tool can cut cast iron pipes up to 8 inches with an impact driver, or up to 4 inches with the manual ratchet. Its lightweight, compact design, 13.5 pounds, 11.5 long, allows easy handling in overhead or cramped areas. The adjustable knob ensures a secure fit on the pipe, while the removable handle and low-profile cutter wheels provide flexibility. Whether using a manual ratchet or impact driver, the cutter guarantees a clean, precise cut. Equipped with a torque limiter, it prevents overloading, ensuring durability for years to come. Sailors aboard the USS New Orleans drop anchor in Cibo Harbor, ensuring a secure and stable position for the amphibious transport dock. This operation enhances collaboration with allies and strengthens regional stability.
The Hitachi EX1200 manufacturing process includes cutting, chamfering, auto welding, final welding, SGS inspection, sandblasting, pipe installation, and premium painting for durability. This heavy-duty excavator is built for demanding tasks such as digging, dredging, and lifting in challenging environments.
Depreto Industries specializes in designing and manufacturing high-performance industrial systems, offering customized solutions for various sectors. Their expertise ensures precision and efficiency in production. Watch as advanced robotic technology transforms the welding process for automatic guided vehicles, AGVs. The journey begins with offline programming using Valk Welding's DTPS software, followed by the precise welding of 600 meters of seams on each 18-ton AGV. Equipped with quick-touch sensing, the robotic system ensures perfect alignment and corrects any material deviations. The entire process unfolds in 3 stages: loading, cutting wire to size, and executing seamless welds. This efficient and highly accurate welding technique sets new standards in AGV manufacturing, increasing production speed and ensuring long-lasting durability. Experience the precision and expertise involved in generator, stator, and rotor repairs. The process starts with detailed stator rewinds and bar installations, followed by full assembly. Each component undergoes rigorous electrical testing to ensure flawless performance. Rotor windings are carefully balanced at speeds up to 4,150 RPMs, while parts are machined using advanced techniques. Ferroarm measurement technology ensures precise component alignment. The entire process is carried out in an ISO-certified facility with high-speed balancing capabilities up to 50 tons, along with CNC machining and in-house NDE testing. The facility also offers a full range of generator services, including custom solutions for unique repair needs. Skilled technicians leverage years of experience to troubleshoot complex issues, ensuring every repair is precise and efficient. This thorough, high-quality process ensures that every generator repair is completed with industry-leading turnaround times and exceptional reliability, maintaining peak performance for even the most demanding applications. At Schmidvoraus Groditz GmbH, the forging process for high-performance products used in the energy industry begins with molten steel produced in an electric arc furnace, generating up to 50 tons per batch. After alloying and fine-tuning in the ladle furnace, the steel is cast into blocks. The blocks are then forged under high pressure using a 60 meganewtons press. Heat treatment follows, including water and oil quenching to enhance strength. Once the components are forged, they undergo ultrasonic and mechanical testing to ensure the highest quality. After thorough inspection, the products are marked and dispatched, ready for use in demanding energy applications. The industrial gearbox rebuild and repair process begins with a comprehensive inspection to assess the condition of the gears. Components are carefully disassembled, and any worn or damaged parts are replaced or repaired. The gears undergo precision machining, ensuring they meet strict quality standards. After assembly, the gearboxes are rigorously tested for performance and durability. The process includes high-quality coating and finishing, improving the longevity of the components. Finally, each gearbox is thoroughly inspected and ready for use in demanding industrial applications, ensuring optimal performance and reliability. Advanced testing methods, such as load testing, are employed to verify the gearbox's ability to perform under pressure. The facility's expert engineers utilize cutting-edge technology to enhance the repair process. Throughout, attention to detail and quality control ensures that each gearbox exceeds industry standards. Each gearbox is then carefully calibrated to match the specific operational requirements of the customer's machinery. The production of a complete crane hook block begins with the careful selection and cutting of raw materials. Once the materials are prepared, the process moves to upsetting and drawing out, shaping the metal to the required specifications. The next step involves heating the material to the necessary temperature, making it pliable for bending. Bending is followed by precise forming to achieve the desired hook block shape. After forming, the piece undergoes trimming to remove excess material and ensure a smooth finish. Once the basic shape is complete, the hook block is heat-treated to enhance its strength and durability. This is followed by machining to refine the dimensions and ensure it meets strict quality standards. To protect the metal from rust and corrosion, a rust prevention treatment is applied. After the treatment, the hook block is carefully packed and prepared for shipping. The hook block is then placed under packing for secure transit, ensuring its integrity during transport. It is carefully loaded into the shipping container and dispatched to the client's workshop. Upon arrival, the block is assembled into 2 complete hook blocks, ready for installation and use in demanding industrial operations. Each hook block undergoes final inspection to ensure it meets performance requirements. The entire process ensures that each hook block is manufactured to meet high standards of quality and performance, ready for heavy-duty use in the client's operations. Finally, the completed hook blocks are tested under operational conditions to guarantee their reliability and functionality. The production of spherical roller bearings starts with high-quality heat-treated components sourced from global suppliers. The inner and outer rings are carefully ground to achieve the required surface characteristics, ensuring smoothness on both the sphere and outer diameter. The first step in processing involves grinding the ring faces, followed by cleaning and drying to remove any dust or debris. Once cleaned, the rollers, guide rings, and cages are carefully assembled with the rings into complete bearings. To preserve them from corrosion, the bearings undergo a protective treatment before being packed and shipped. Finally, the bearing designation is laser etched onto each bearing for identification. This rigorous process ensures the durability, reliability, and efficiency. These bearings are shipped worldwide, with the facility producing approximately 3 million units each year. The self-aligning design of spherical roller bearings allows them to accommodate misalignment and heavy loads. This makes them ideal for demanding applications such as mining, construction, and industrial machinery. Their long service life reduces downtime and maintenance costs. This video documents the hot forging process at ILSAM, where steel components are crafted for tractors, heavy machinery, industrial vehicles, and hydraulic systems. Each step is designed to ensure structural integrity and dimensional accuracy. Production begins with raw steel bar selection, followed by preheating in industrial furnaces to achieve the necessary forging temperature. Once heated, the steel is shaped using double-action hammers exerting forces up to 3,000 tons, and both screw and crank presses reaching 2,000 tons. These machines deform the steel into rough shapes with high impact and speed. Before machining, forged pieces are cooled under controlled conditions to prevent internal stress and distortion. Forged parts undergo mechanical machining for precision, milled, lathed, or planed using CNC systems. Heat treatment is then applied to improve hardness and durability, adapting each part for its specific application. Mold design and development are handled in-house, combining CAD/CAM software with hands-on experience. Highly specialized technicians monitor all operations, from modeling to machining, using vertical mills, automatic lathes, and profiling tools. ILSAM's workflow integrates modern technology with technical expertise, ensuring consistency and performance in each steel part they produce. Laying railway tracks once required intense manual labor, but modern machines have transformed the process. This specialized track laying machine picks up concrete sleepers and places them onto the prepared rail bed in precise intervals. Steel rails are then laid on top, aligned, and clipped into position. A follow-up unit adjusts alignment and tamps the ballast underneath for stability. These machines can lay hundreds of meters of track per day, drastically improving speed and efficiency. Each movement is synchronized to ensure safety and accuracy throughout the entire operation. The video presents the intricate assembly, testing, and deployment of the Palmieri TWM's 500-15 advanced machines designed for tunnel widening operations under active traffic conditions. Built to expand tunnels from 2 to 4 lanes without halting normal road use, these machines are a key solution for modern infrastructure upgrades. Assembly begins at the factory, where each component is carefully mounted and aligned. The TWM's 500-15 consists of 2 self-propelled systems, the PCM 500 pre-cutting machine and the SPM 15 segment placing machine. These units operate in alternating cycles, one preparing the tunnel face, the other reinforcing it, allowing a seamless, continuous process. Each machine undergoes a modular assembly process to simplify transportation and reassembly on-site. Components like hydraulic lines, support frames, and cutter heads are pre-tested to ensure proper integration. Technicians work in synchronized teams to reduce setup time and improve accuracy across units. The PCM 500 initiates the operation by performing a semicircular pre-cut along the tunnel wall, using a blade 8.5 meters in length and a cutting width of 500 millimeter. This unit works on RCK 200 grade concrete and simultaneously consolidates the structure with specially formulated grouting material to stabilize the excavation face. Special attention is given to maintaining alignment during the cutting phase, as any deviation could impact the structural integrity of the expanded tunnel. Sensor arrays monitor blade positioning and torque feedback in real time, allowing for automatic adjustments mid-process. Following demolition and debris removal, the SPM 15 begins placing concrete segments to form the new tunnel lining. This segment placing machine, with a maximum load capacity of 15 tons, operates within short traffic interruptions, typically not exceeding 6 hours. It installs precast segments to form a new tunnel arch around the expanded space. Segment installation is aided by hydraulic clamps and articulated arms, enabling precise placement even in confined underground environments. Alignment lasers assist the operator in maintaining correct curvature and spacing throughout the lining process. Testing at the factory includes full operational checks on cutting strength, load handling, and machine mobility. Simulated runs ensure that each unit meets field requirements before transportation to the job site. Once on location, the machines are reassembled and integrated into the tunnel environment, such as the Montedomini tunnel featured in this project. The combination of powerful mechanical design and smart staging enables these machines to alternate operations continuously. The PCM 500 executes precise, high-force cuts, while the SPM 15 follows closely with structural assembly. Together, they provide a rhythm of excavation and reinforcement that eliminates delays and increases throughput. The entire process is designed for efficiency and safety. Average daily production reaches up to 1.5 meters of completed tunnel. Because the system allows for controlled, phase-based work, construction can continue with minimal disruption to traffic. From design to deployment, every step reflects a commitment to engineering precision and adaptability. These machines are not just tools, but systems tailored to meet the demands of modern tunneling, especially in high-traffic zones where downtime is not an option.